Where does the formula for vector field curl come from? So let's look at a 2D case. So we have a vector field here, and it's pretty common to express the x part and y parts as p and q. Different people use different letters, but that's pretty standard. And what I've constructed here is we're looking at the xy axis. You can see we're looking straight down from z here. And I have made kind of a perfect scenario here with a center point, and then the vectors are curling counterclockwise. And so kind of a perfect curl scenario. And let's look at some characteristics here. So if we think about, and we have to remember that both x and y are dependent on x and y. So p, the x part, is dependent on both x and y, and same with q. So if we look at, so I've constructed these four vectors here, and if we look at the q ones, well, they have a y component, but no x component, or p component technically. And so we need to think about what is happening to q as x moves. We don't look at q as y moves because q basically has the same movement as y. But let's look at how q moves as x moves. So as we're going positive for x, q goes from being negative to being positive. So a slope that's going from negative to positive is a positive slope. And then if we look at p, so that's the x part, and we would want to look at p, partial p partial y. So if we look at the p's, so this is a negative x value and a positive x value, and as y goes positive, what happens to p? Well, p was positive and it turns negative. So a slope going from positive to negative would be a negative slope. Okay, well, now we just take these two things here, and let's take the partial q partial x, and we want to make them both positive. Well, this already is. So let's subtract this thing, because when you subtract negative, it turns it positive. And so basically, if you take this thing and it's positive, it tells you that there's going to be a positive or counterclockwise curl. So this is the 2D formula. Let's think about 3D curls. Now, 3D curl is a vector. 2D curl is just one of the components. It's the z component of the vector. This is what we just derived. We're looking straight down from z, seeing how x and y interact. And what we do is we think of a vector that, and kind of where we're going, let's just look here. So 3D vector field curl is basically a vector, like the red arrow there, where if your curl is mostly acting like vector swirling in this direction, that your curl vector is normal to that. So if we think of what we did, and we think of this being some number that determines the z component of the vector. So this is a vector coming straight out of the xy floor, straight at us, normal to that floor. And of course, the tighter the curl, the longer z is going to be. And then we just do that two more times. We do one for the x and one for the y. And so let's look at the x one. We would derive it the same exact way. This would be our 3D vector field, and this would be the 3D vector, a 3D vector, the curl vector. Okay, well, So when we're thinking about x, we're staring straight down from x, and here we're staring straight down from y. And when you derive these, you have to make sure you do the same exact thing with all of them. When the first one we did, we were staring straight down from z, just like we are with these two. If you don't draw them the same way and using exactly the same logic, you can easily get them going the other way than what you thought you were. So if you derive this, I recommend just draw them exactly like I am. Draw it like this, and then the vertical one is kind of popping out at you. Okay, well, so Q is Y and R is Z. And basically for the X component, we're thinking of how Y and Z interact. And so here we're kind of thinking of partial Z partial Y, and here we're kind of thinking of partial Y partial Z. That's just what we did over here. And so if we make our perfect little scenario counterclockwise or positive curl or rotation, well then R is kind of like Z, so we can see these going along with Z, and they only have a Z component. And so if we're thinking of Z partial Y, or we're gonna call it R, so partial R partial Y, what's happening with these as Y is moving in the positive direction? Well, R goes from being negative to positive, which means it's going to be a positive slope. And now if we think of Y partial R, so Q is moving in the Y direction. So what happens to the Y direction as we're moving positively in the Z direction? Well, it goes from being positive to negative, and so it's a negative slope. And so we do exactly the same thing. We take the positive one, and I'm looking at the wrong one here. We take the positive one and we subtract the negative one, and there we go. Okay, and I won't take time to go through the Y one. You can kind of look that over yourself. But next, let's think about how we actually compute this. So to calculate this, so here I have the vector we just derived, and here it is again. It's just written a different way. But this would be hard to remember, but you may kind of recognize it as it kind of looks like a cross product. And so if you just think of a cross product, you don't have to remember anything. We're not doing a literal cross product, but we're doing something almost exactly like it. It is the same as far as the order we do stuff and stuff. So I'll show you what I mean. So basically, if you were going to take a cross product, and I'll include a link to my cross product video if you're rusty on the cross product, but we normally think of our two vectors as these two. We put them in a 3x3 matrix, and we take the determinant of it just like we would a cross product. And if you were going to take a cross product, you'd put ijk for your unit vectors in each direction. You'd put your two vectors that you're crossing here, and you'd take the determinant. Well, what we do is the same thing, except these are the components of our vector field, and these are the del operators. We're kind of doing a cross product of the del operators and in the vector field, if you want to think of it that way. It can be a little confusing because so if you've done a determinant before, you know that the 3x3 determinant, you take this, which is here, and multiply that by the determinant of this. And then you take this and do the determinant of this, and then this and the determinant of this. So back to I. So if we do the determinant of this, here's the idea. So we need to get this partial R partial Y. Well, here that is. Now this is not multiplication. Okay, that's what's different about a real cross product. This is just a memory aid. Basically, the idea is you take the R and put it here, and there you go. Okay, so you're doing partial R, partial Y minus partial Q, partial Z, because you would put the Q up here. And there you go. And the first one is ready to go. Then, now you may remember with 3x3 determinants, I is positive, J is negative, and K is positive. And so if you do it that way, we would be doing like this. So we'll look at this first, and then I just flip it around here. So that's really the only difference. But I went ahead and put the minus here. And then if we do partial R, partial X, there we go. And then minus partial P, partial Y, and there that is. And then if you distribute the negative so you can make it a plus, well, then you just end up switching these two. So it's just easier that way. And then the same thing with this. So that's really all there is to finding this vector of 3D curl. Is just remember the determinant, and that's how you do it. And I think that's pretty cool. I almost forgot I was going to do an example. So we have our vector field here in our PQR elements, and if we want to take the find the curl vector, well, then we're going to cross the del operator with the vector field. And so here we have that. So this is our kind of pseudo del vector, and this is our PQR vector. And now it's just like taking a cross product. So this first one here is just going to be I times the determinant of this. So we do this, but again, it's not multiplication. It's this placed up here, so we can take the derivative, and that's here. And then we put this up here, and that's here. Then when we come to J, remember this would have been negative. But if we want to make it positive, we can just reverse the order. So instead of doing this minus this, well, then we'll do this one first minus this one. And so if we put the y squared z up here, we get this. And then if we put the x plus z up here, we get this. And then for the last one, we're doing the determinant of this. So we put this up here and get this. We put this up here and get this. And now we just need to do all these derivatives. So x plus z with respect to y is going to be 0. 3xyz with respect to z is 3xy. Y squared z with respect to z is y squared. X plus z with respect to x would be 1. 3xyz with respect to x would be 3yz. And y squared z with respect to y would be 2yz. And so now this basically is the vector, but we need to clean it up. Plus I wrote it in a different way too. I kind of prefer this method for a final answer. And so here we just dump the 0. We put 3yz's minus 2yz's as a single yz. And there is our curl vector.